but just we won't bring up any grades or anything. So if we have questions like that, just wait till I turn the recording off. Guys, just one question popped up from Lara. It's about p-value, about how to find it, and so I figured that's a big question a lot of people have. So we're going to kind of go through some examples of doing that. So one of the things, and Lara, I'm speaking mostly to you here, and anybody listening to the recording, if you want questions on just specific types of things, the best place to go in MATLAB is the study plan. You can look back at your past homeworks, but they're like closed where you can't input answers. But if you go to the study plan, you can look up questions on anything. So if I go to study plan, and then when it pulls up here, you'll have a lot more on your side than I will. I haven't done the homework, right? So you will have a lot more stuff here. But one thing you can do is just click all chapters. And when you do that, it pulls up, every chapter. So you can go, you got to know where the specific question is in terms of the section out of the book. But let's say we're just going to do some hypothesis testing stuff. So we'll go to chapter 10. So I'll do a population proportion, right? You can click on that. And then here are a couple of different things. And this is the one that we really want to focus in on, is test hypotheses using a population, or about a population proportion. And there's a drop down here, and you can kind of switch between the things that were just available. But I'm going to stick on this one, and it leaves these questions here. So all of these are about testing a population proportion. So I'm just going to click on one of them and see what it says. So let me say this in general about the p-value. No matter what kind of tests we're running, the p-value is always the probability that the null hypothesis is true, given that I just got tongue-tied. The probability that the null is true, given the information that we got in our sample, or samples, whatever that is. So the basic logic of the p-value is, look, we know even if the value or the thing that's going on in the null hypothesis is actually true, when you go out and get a sample, you don't expect the sample to match the null perfectly, right? So in this example, actually I want one with context, so it's easier to talk about. It's a lot of words. I don't want to read all that. Okay, so this one's a little bit easier. Oh, a lot of words? Okay, then we'll go back to that one. We'll do that. Okay, so give me a second to read this. Right, okay. So the null here that they're setting us up for is this right here, that the population proportion is equal to 50%. So, if we reach in and grab a sample, we know, and it looks like they're using 300 companies. So if you reach in and grab a sample of 300, even if the true population proportion is 50%, we don't expect to get exactly 50% in every sample that we ever grab. It's like taking a coin and flipping it. The probability of heads is 0.5 or 50%, but you don't expect to get it exactly 50-50 every time. That's called sample to sample variability, and we expect that. So the question becomes, when you go out and grab a sample and it's not what the null is, how far away from the null is it? And is that so unlikely that we think that the null is wrong? So that the p-value is the probability that we get what we get in our sample, given that the null is true. Because again, it goes back to that. We don't expect to get 50% every time. In this case, it looks like we got 153 out of 300, which is a little bit higher than 50%. But the question becomes, did we just happen to get a little bit higher than 50% by chance? Or is it really telling us that the number is not 50%, the true number is something that's higher than 50%? And I think that if you said, hey, we looked at 300 companies and 153 of them were considered winners, sure, that's just over 50%, right? I can get the number for you. So 153, right, divided by 300 is going to be just over 50%, right? 51%. But is that really telling us that it's the true number is higher than 50%? Or is this one of those cases where we just happen to get a number that was on the high side of 50% because we know we're not going to get 50% every time? And I think that only getting 51% is going to, we would say, look, that we expect that kind of variability to happen. And the p-value backs that up. It says right here, you can see the p-value is already calculated. With a p-value of 0.36, that's a pretty high probability. Given that the null is true, that it is 50%, us getting 153 out of 300, which is 51%, happens about 36% of the time, given that the true number is 50%. And that's just too high, right? We're just saying, oh, we just happen to get a high number by chance. So we're going to have to not be able to overturn the null value, right? We're going to say there's not enough evidence to support the alternative, which basically means, look, we're going to have to go with the null right now because we don't have enough evidence to overturn that. Right? So that's the logic of the p-value no matter what type of test you're running. It's always about assuming that the null is true, how likely is it that we get what we got in our sample or samples? Because we don't expect our sample data to match the null exactly. We always know that it's always going to be a little off. The question is it a little off by chance, or is it off so far that we go, man, that null probably isn't true, right? So calculating the p-value, right, they've already done this for us, but we can do this one and find that p-value. So let me see if I can get StatCrunch to fit on the screen here. Where did I put the other? There it is. Okay. So this is a proportion hypothesis test. So I go to stat. This is a proportion stat. We have one sample and we have summaries. We don't actually have the 300 companies. So we have summary, and we had 153 successes. We had 300 observations. The null is that it is 0.5. The alternative is that it's greater. They just said that in the problem. And then we should get a p-value of 0.3645, and we did. It's the same one that they got. Is that okay? No, don't apologize. I totally understand. Okay, so that's that kind of example, and all of them are going to be pretty much that. You just got to know where you're going. So the places that we would have gone so far, and let me expand this a little. So that's a proportion stat. So you go to stat, proportion, one sample, and then you're always going to go to summary here. You'll never have the data. You could go to two sample, which is where that's in chapter 11, and I can show you an example of that. The other places that you would go is T-stat, which is one sample, again, for chapter 10, two samples for chapter 11. And then the other case is where, in chapter 11, where you had the dependent case, but you still go to T-stat, ends up being a one sample one. And then there's also the goodness of fit, right? That's the chi-square test. And so there were, those are you got to know where to go to do each type of test, if that makes sense. And that's kind of what I was getting at in one of those discussion areas, is saying, hey, how are we deciding what test we're running? Because it's not going to come out and say, hey, don't, make sure you use a proportion test here, right? The chi-square test. Right. So the thing that I usually tell people for these types of tests is to ask yourself, is the question a qualitative question or is it a quantitative question? And usually there's other keywords that tip that off. So for example, if we look at this one, think about the question that we're asking the people in the poll. So in a previous poll, 31% of adults with children under the age of 18 reported that their family ate dinner 7 nights a week. So even though there's a number there of 7, the question is actually being asked, do you eat dinner with the family 7 nights a week? And the responses to those questions have to be yeses and nos, right? The people responding could not respond with a number, right? Because if you said how many nights do you spend eating dinner with your family, that's different. That is a quantitative question. But in the way that they phrase this question, you're asking people, do you eat dinner with your family every night? And they can only say yes or no, right? I mean, I guess they could say sometimes, but in either case, they're not responding with a number, with a quantity. If they said 4, you'd be like, what are you talking about? That's not what I asked you. So if it's a qualitative question, you have to be dealing with proportions. And like I said, there's usually other keywords that are tipping you off to think, oh, I'm going to do a proportion, some sort of test with a proportion. Now, again, on your exam, it's not going to have all these words at the top, right? It's not going to say, hey, by the way, you're testing proportion. But notice that it does say proportion in the problem, right? And then also you see these percentages running around. With quantitative questions, you won't see percentages because that's not how you organize quantitative data. You can't, if I said how many nights, do you eat dinner with your family? You're going to say 0, 1, 2, 3, 4, 5, 6, or 7. I can't really take a proportion of those. I could do relative frequencies, but generally, if I'm interested in some sort of aggregate number, meaning some way to summarize all of the data, I'm going to take an average or a median or something like that. So that's one of the things I say is look at the question that you're asking, that the question is asking the participants or the things that you're getting data from. Is it qualitative or is it quantitative? If it's qualitative, you've got to be doing some sort of proportion test. If it's quantitative, you've got to be doing some sort of t-test. So, for example, if we go back here, I guess I should have just clicked all chapters to save some time. So if we go here to chapter 10, and notice we're still doing a hypothesis test, but notice I'm going to look at some that have means. Now, obviously, in here, it's going to tell us that we're working with means. But I want to, forget that they're telling us all those details. Just look at the problem, and you're going to notice you're not going to see, let me get one with context. You're not going to see percentages floating around because that's not how you summarize quantitative data, right? Like you'll see the word maybe mean or you'll see the word average, but no, there's not going to be any mention of proportions or percentages here. So again, that will be a pretty big filter for which type of test you're going to run in StatCrunch. Because again, when you're in StatCrunch, you go to stat, and then the only places that you'll really go are t-stats and proportion stats, again, besides like the goodness of fit. And the t-stats are the quantitative when you're talking about averages, means, things like that, or proportions where you're talking about, a qualitative question or you have some sort of percentage. And then the other thing that's the divider is how many samples did you take? So with t-test, you're either 1 sample or 2 samples. With proportions, you're either 1 sample or 2 sample. Does that make sense? Okay. I can show you an example of each type if you want to do that. So like for this one, right, it's saying several years ago, the mean height was 67.3. We're curious if, well, that already gives us the p-value. Let's have one that doesn't give us a p-value. Okay, here we go. So I'll give you a second to read that, wrap your head around the context. Okay, so again, thinking about the p-value, they tell us that the average score is around 24. We got 24.3. So, the question is, is 24.3 really higher than 24? Or did they just happen to get higher than 24 by chance? Right? So like that sample to sample variability, or is this actually showing a significant difference from 24? I think we'd probably know that it's not going to be. 24.3 is not far from 24, especially with a standard deviation of 3.7. So I expect a p-value that's higher than 0.05 here. But let's go through it. So we're talking about an average, and we're always talking about parameters. So this is always going to be population stuff here. It's always going to have to be equal here, and we're going to have to assume that it is 24 until proven otherwise. So again, here, and we're asking greater than, I believe it says somewhere, you're right, they're saying, are they college ready? Which means higher than 24 in this case, right? That is, are they scoring above 24? So that's greater than 24. Oh, somebody just entered. Okay. Yes. Yeah, okay. So we should be good there. And you're always going to satisfy the requirements. Okay. Now the test statistic and the p-value are all going to come out of StatCrunch. So I'm not going to worry about finding that on its own. So I'm going to go to stat. This is a t-stat, and notice that it's giving you a t there, right? That should tip you off like, oh, we're doing something with a t. One sample, we have summary. Sorry, that's barely fitting on the screen. Summary. And then they tell us 24.3. I don't quite remember the standard deviation. 3.7. And we have how many people? 200 people, right? 200 people. The null was 24. We're talking about greater than. We don't have to change the confidence level. We're going to use an alpha of 0.1, so it tells us that. But all of this would come out of the analysis. So there's your t. There's your t statistic, and then there's your p-value. So the p-value, like I said, is bigger than our 0.1 in this case, right? I said 0.05 earlier, but it's bigger than 0.1. And therefore, this is not enough evidence to support the alternative. This is not enough evidence to say that the students, on average, are college ready. Who entered? Somebody came in. Oh, Tonya, can you hear me? Okay, great. I didn't know who it was. So Tonya, Lara was just asking about what, we kind of talked about what a p-value was, talked about kind of like when to use which type of test, and I was just showing an example of using the t-test. Lara, that seemed to be your big question. Right. Mm-hmm. Right. And this was something else I'm thinking about that came up in the discussion, is that there's two approaches to hypothesis testing. One is what's called the classical approach, and you can see that here in Part C. They're actually calling it that. But it's dealing with the test statistic and the critical value. And the other way is the p-value. Now, everybody generally prefers the p-value way because then it's just, okay, p-value, compare it to your alpha, and you're done. If the p-value is below alpha, you reject the null and accept the alternative and say there was enough evidence. If the p-value is bigger than your alpha, then you fail to reject the null and you don't have enough evidence to support the alternative. So that's generally a lot easier way. The problem, old habits die hard. The test statistic and the critical value way was the way of old. Because if you don't have a fancy calculator or a fancy software like StatCrunch, calculating the p-value is pretty cumbersome. You either have to have a table or you have to do calculus to do it if you don't have software. So that's why a lot of people went with the test statistic and the critical value. But now that we have software, p-values is pretty easy to come by. So I don't want to get bogged down in things you don't want to talk about, but I can find the critical value for you if you want. and talk about how to get the same decision, right? We know that we're failing to reject because our p-value is big. But this means that if we do it the test statistic way, my test statistic is not going to fall in the critical region, or it's not going to go past the test statistic if we do it that other way, if that makes sense. So I don't know. I don't really know where to go next. What would be helpful to you, both of you? Right. Yeah, so I get that the wording is kind of wonky. People don't usually say "do not reject." That's not like a flow of words that people generally use. It's just kind of the right. You're kind of stepping into this world, and this is the terminology that's used there, right? It's just like any other subpopulation, right? They have their own like ways of talking, and that's just kind of the language that has stuck around in statistics, either rejecting the null or failing to reject the null or do not reject the null. Again, this doesn't matter what type of test that you're running. If you're talking about the p-value way, which is the way that most of the time we're talking about it, if the p-value is below your alpha, right? If the p-value goes below it, that means you reject your null and you accept your alternative. Therefore, there was enough evidence to support the alternative. If your p-value is above your alpha, then you simply fail to reject the null and you don't have enough evidence to support the alternative. But that last piece is always in terms of the alternative. Maybe I should type that out. Hang on. Sorry, I'm trying to get a new document pulled up. Okay, wait. So, yes, write that out or don't write that out? Oh, okay. So you're good with that. Lara? Okay. hmm I'm wondering if this will do it. If this question, it just has multiple parts. I don't. Why is it taking so long? It just changed the numbers on me. I was gonna see if this one did it. So let's see, 3.5. And I hope this is not a waste of time because I don't want to. Let's see, greater than, I think it's still greater. Okay, so let's see. So there is that. So null equal 24 greater than 24. These are going to check. This I'm going to have to look up. So the degrees of freedom here are 149 because there was 150 people. And we're asking about greater than, we need 10%. So 1 point, what does it want? 2 decimals, 1.29. Uh-oh, what did I do wrong? Degrees of freedom, 150. We need a 10%. What am I doing wrong? Oh, they want the test statistic. I'm sorry. So 1.75. Okay, so this is identify this. That's going to be the number right here. Am I going too fast? Okay, so this is a one-tailed test because it's simply greater than. So I have my 10% all in one tail, and so that tells me that it's 1.29. And it's the greater than sign. I don't think that it shouldn't have been asking you a lot about the critical value and test statistics. We've tried to eliminate those. Is this the so don't get too caught up. So, but this is what you're talking about. Okay. Right. Okay. So let's look at our p-value. The p-value is lower than alpha. Yes, we're okay with that. Okay. So 0.04 is lower than 0.1. So we're going to reject the null. So right. Now this one doesn't actually ask us to say anything about the alternative other than the interpretation part. So no matter if you reject or fail to reject, starting this sentence right here is going to be part of the problem, whether or not you reject or fail to reject. And notice that it's always going to be in terms of the alternative. So even if I didn't know the answer to reject or fail to reject, I'm going to put greater than here because that's what's in my alternative. It's always in reference to the alternative here. And then the only thing I need to fill in is if there is or is not. And we do have enough evidence. There is enough evidence to support the alternative. And so if the p-value was high, which it's not, but if it was high, then I would change this to do not reject, and I would change this to is not. That would not change. So these two things should always coincide. If you're going to say do not reject, then you're going to have to say you don't have enough evidence. If you're going to say you reject, you've got to say there is enough evidence. But this right here is never going to deviate from being whatever the alternative hypothesis was. So it's, again, I oftentimes bring up the example of a jury trial because it's, hang on, let me go get my charger. Hang on just a second. My computer's about to die. So the jury trial is a really nice analogy for hypothesis testing. So when you have a trial, there's always evidence against the defendant, right? Or you wouldn't have a trial. And so the question just becomes is it enough evidence? So when you go into the jury trial, you're assuming that the person is innocent, but there's the possibility that they're guilty. And so all you're basically doing is do you have enough evidence to reject your initial assumption of innocence and conclude that they're guilty, or do you not have enough evidence to reject your initial assumption and you just conclude not guilty? So, but notice when I say my conclusion, it's always in terms of guilty, right? There's enough evidence to say guilty or there's not enough evidence to say guilty. We never say innocent. So the point I was trying to make is it should always be in terms of the alternative. But yeah, I totally get the wordsmithing that's kind of happening here. We don't generally like grammatically say, reject or do not reject. I know that's kind of wonky. But in terms of how these things should align, rejecting always means you had enough evidence. Failing to reject or do not reject always means you didn't have enough evidence. And then it's always... What do you mean by backwards? Like, how would you say it? Wait, I'm sorry, I couldn't hear you. Say it one more time. You're rejecting the null because you had enough evidence to support the alternative. Yeah, it's about what you're. I understand that, but the thing is we got to wrap around what the evidence is for, right? And again, in a jury trial, evidence is always presented in terms of the guilty part, right? The defense may try to um, contradict that evidence, but the evidence that's presented is always against the defendant, right? There's never evidence for innocence, right? That there's no such thing. Like, how do you prove innocence, right? So think about, the evidence that you're presenting is always for the alternative. And the question just becomes, is it enough? Is it overwhelming that you're going to have to reject your initial assumption, which is the null? Or is it not enough and you're not going to be able to reject the initial assumption? So I get what you're saying, right? Rejecting, you would think, I guess you're saying should be not enough evidence. Is that what you're inclined to think? Right. And it really is going to, what are we talking about? And it really comes down to what is that p-value? What is it about? And it's always about evidence towards the alternative, always. Yeah, that works. Right, right. And, to be honest, that's how things are actually. Sorry, I'm just reading somebody else is trying to get in. I just wanted to know whether the meeting's started yet. Can't see other participants. Sorry, somebody else is here, maybe? They just emailed. Hang on just a second. Okay. I don't know. Right. And so, you wouldn't really have these things separated, right? If you ever read a statistical project, meaning just one that did some sort of analysis, they're not going to go through all of this stuff, right? Like it's going to be, they're going to say, here's what we were testing, here's our p-value, and here's what we say because of that, right? They're not going to go through this like step-by-step process. But this is, behind the scenes, they are, right? They are kind of going through that, and which is why you're being forced to do it as well, because that is kind of the process of doing it. But I get that it's you don't get it all like together, right? It's not all in one little spot. So the majority of the final is going to focus on chapters 9 through 12. Um, Sorry, I'm still trying to talk to this other person too. Um, it's going to focus on 9 and 12, but there are going to be questions dating back to chapter 1. So I would focus on the big ideas that are in all the chapters from 1 through 8, but spend most of your time focusing in on chapters 9 through 12. Hypothesis testing and confidence intervals. And right, the last couple of weeks. So that's probably like the second half of the class is probably right. I think that's where chapter 9 starts, probably in like week 5. Right, everything that we've done has been to push towards hypothesis testing, like everything. So, when we were in chapter, all the stuff from chapter 1 through 7 basically was all to prep us for chapter 8, right? Which is why it was only 2 sections in a whole week. And then all of that was to set us up for chapters 9 through 12. to get this idea of, what is the central limit theorem, and then um, how likely are things to happen in that sampling distribution based on some certain criteria, and then to set us up for this formal hypothesis testing that we're doing in the rest of the chapters. Somebody just logged in. Hey, nope, now they're gone. Okay. Anyways, I don't know. Okay. Other thoughts, questions? Yeah. Oh, there they are. Yeah, so I would focus on getting, having like a really good example written in general. Focus on those things, right? So if the wording is messing you up, write one example out of saying, like just like this one down here at the bottom, say, okay, this is what it looks like here. And then the only other option is that this changes to do not reject and this changes to is not. But those should always be parallel. Reject with enough evidence, failing to reject, or do not reject with not enough evidence. Okay. Sure. Tonya, anything else? Okay. Gotcha. Yeah, and I totally understand that. Totally get that. Okay. Bye, Lara. Krupa, am I saying that right? Can you hear me? Can you hear me? Okay. Krupa, again, I hope I'm saying that right. I saw your chat. Can you turn your audio on? Do you have a mic? Something is wrong in my computer. Okay. So yeah, can you help me with chapter 12? What do you mean by that? Okay. Sure. No problem. Guys, we're listening to the audio or the playback of this. I'm just waiting on Krupa to see if she can get her mic to work. Hey, I can. Okay. So I'm recording the session, and so I don't want to pull up your homework because then everybody will see your grades. Does that make sense? So we can go to. So what I was telling them before was that you can review anything by going to study plan, and then you can simply click all chapters. And if you want to do something in say chapter 12, you just scroll down to chapter 12, and then you're saying you're in 12.1, right? Okay, give me just a second. Let me do it so I can pull up the homework. That's not so today is the 12th. Okay, let's try this. Number 2, is that what you said? Okay, so let's see what number 2 is. Okay, so this is like I said, this is a goodness of fit test. So what you're basically testing is, does your proportions from your sample, do you have enough evidence to overturn that it came from some sort of stated distribution? Um, so what I mean by that, so let's see what it says. A company states that 13%. Okay, so the company is stating that in a bag of candy, it looks like that the proportions of the different colors should work out this way. The null is going to have to be that is the case, right? That's what it is. So you're going to have to assume in the null that it's stated as the same as the manufacturer. So right. So it looks like it's going to have to be B, because you're going to have to assume that what is being stated is true unless proved otherwise. So they're stating that it's this distribution, 13% brown, 14% yellow in all those. And you're just going to have to say, okay, I'm going to have to go with that until whether or not I have enough evidence to overturn that. So here I'm going to have to say, okay, we assume that it is true what they said, and then or we say it's not that, right? And so that should be our answer there. And so, right, so okay. So all this is this is going to be a frequency of each of a relative frequency of each category. So the first thing that I'm going to do, so the numbers that you're seeing here are, right, compute the expected counts for each color. So I'm assuming, oh yeah, so he counted the number of candies for each color obtained in the results in the table. So this information right here is from a sample. Now, we don't expect the counts to be perfect, right? We don't think that the company painstakingly goes through every bag and makes sure that it's exactly 13% brown and exactly 14% yellow, but we think that it's close to that. So the first thing I'm going to have to do is I'm going to have to add these numbers up, because I got to figure out how many things were in the how many pieces of candy were in the bag. I wish it would tell us that in the problem, but it doesn't. So you're going to give me a second. So let's see. Well, I guess I can do that on screen. Oh, do you already have it? Oh, gotcha. Hopefully we get the same number. Let's see. Yeah, 393. Okay, great. That's what I got. Okay, now the company states, so I'm going to keep that number in mind. The company states that 13% of the bag should be brown. So if we have 393 of them, right? If we multiply that by 0.13, which is 13%, the expected number of brown candies should be 51. Now, it's obviously... Well, okay, so hold on. So I think you're getting two things. I think you're getting two things confused. One is the actual percent of brown candies in the bag. The actual percent of brown candies in the bag is 60 divided by the okay, hold on. 60 divided by 393, which is 15%, which is not 13%, right? Which is why the 60 and the 51 don't match. Now the 51, if this was perfect, right? If you do 51 divided by 393, we should get about 13%, right? Which we do, right? So I got the 51 by saying, okay, there's 393 pieces in the bag. If the company is correct, we should expect 13%, so that's times 0.13. So we expect 51 pieces of brown candy, and there were 60, so a little bit higher. Right, so I'm going to do this for each one. So 393 times, for the yellow, I expect 14%. Right, so times point. Right, so we expect 55 roughly. Oh man, it wants 2 decimal places. Okay, 55.02. Sorry, I forgot what the other one was. 393 times 0.13. So 5109. And I think I can shortcut this a little bit. So if you notice, 13% are supposed to be brown and 13% are supposed to be red. So then that's 5109 as well. This... But you multiply it by the claimed proportion, which is what multiply it. Right, yeah. So I just didn't put. I'm just using the numbers from up here as opposed to using the table. I mean, it's the same numbers. Theirs is way more organized. I'm just looking. Okay, I'm saying, all right, blue is supposed to be 24% blue, right? Which is what's going to be there, right? 24. That makes sense. Okay. So let's see. We can finish this out. 393 times, I'm on blue, so 0.24. So 9432. 393 times, what am I on? Orange, 0.2. So 78.6. And then green is 16%. Oops. 0.16. 6288. Okay. Is that what you were asking? Okay. Oh, gotcha. Yeah, yeah. Mm-hmm. Sure. wish it would let me see something. Can you tell me what it? Can you just read it to me, and I'll find an example that's close to it. Mm-hmm. Yeah, and that was something that we talked about earlier. I don't know when you came in, so you may have not been here when we were talking about that. If your p-value is below your alpha, then that means you reject your null, and you also accept the alternative. Except a lot of the times the questions don't seem to be stating that; they just say, "Sure, right, reject." Correct. That's true. Yes, that is true. So if your p-value is below alpha, then you reject the null and accept the alternative, and that means that you had enough evidence to accept that you had enough evidence to support the alternative. If you go ahead, right. So what was your alternative in the example that you have? Greater than? Okay. And what was your p-value? 0.134. So right. So that means we failed to reject the null, which means we don't have enough evidence to say that it's greater than 100. Right? If you don't reject, that means you just didn't have enough evidence to support the alternative. So at this point, you're going to have, if someone's forcing you to say, what do you think the average of the population is, you're going to have to say, 100, because you just don't have anything else to overturn it. I don't know exactly. Can you see this one? Is this, I don't know if this is going to play out the way the question that you're on is reduced wait time. So that's less than in this case. So I just want to see if we're saying the same thing. Oh, a sample was 41. So this question is asking, did they actually reduce wait times? This one looks like they are, right? So the test statistic is negative 301. P-value of 0.0014. So that's 0.001. Okay, and so here we go. So the p-value in this case is below the alpha, right? Our alpha is 0.05. So we're going to reject the null, so it's got to be A or D. So we're going to reject the null because the p-value is less than, right? So that's our correct answer. Okay, and then therefore, this is what I was telling them earlier. If you ever reject, this has got to be is enough evidence. Correct. Yes. And that really comes down to what the p-value stands for, or what the definition of the p-value is. It's the probability that your null is true and you get your sample data. That's not technically the definition, but for us, it's going to work. Um, Correct. Yeah. And if it's lower than alpha, you had enough evidence. So this may be what your kind of question was, like what's the practical? Do you think the results have any practical significance? Let's see. Yes, because two times there is. Yes, because there's. Okay, so that can't be right, right? Because it says no significant evidence, so that's out. This one's out because it says no significant evidence. So let's see. No, because there is while there is significant evidence that shows the new policy is lower, the difference between the previous mean weight time and the new is not learned to be considered important. I don't. There's a difference between the two mean wait times. Uh, mm-hmm. Correct. Right. To me, it's got to be A. And the reason I say this, and watch it is tell me that I'm wrong, but I'm pretty sure it's A because here it says while there's evidence that shows the new policies were effective in lowering the mean wait time of the customers, the difference between the previous mean wait time and the new wait time is not large enough to be considered important. I can see their point, but we don't know the we don't know the average. We don't know the new average wait time. We have a sample, right, which is different than 42, but I don't know what the actual average wait time is. Does that make sense? Like I don't know what it is. I have a sample, so what it's gonna say. Maybe I'm wrong. See, I don't know. I see their point because 41.2 is not that much smaller than 42. So they're saying based on this that it's not large enough to be considered important. And I guess that my argument would be, I don't know, like a second may be a long time for wait time if you do it multiplied by 300 people trying to get on a plane. Um, so I see their point why they're saying D. I guess I have my reservations about why they're saying that it's D, but okay. Um, if it's something like that on your test and you're reviewing it and you're going, hey, I got a difference and I think that's enough, just email me and I'll be happy to look at it. Because to me, sure, a second is not a long time, but if you do that by if you multiply that by a big number, it adds up. So I don't know. I would be okay with A there, that there is a practical difference, especially if there's, if seconds cost money, then we just saved one of them. Yep, good with that. Yeah, and a lot of people say if the P is low, reject the hoe. A lot of people say it that way to help remember it. And so we mean lower than alpha, right? Lower than alpha. That's it? Okay. All right. Well, if there's anything else, don't hesitate to reach out. All right. Have a good day. All right.